can ask your question. So with this, we'll start with radar basics. So my name is Rachel Gutierrez. I'm a meteorologist at the National Weather Service in State College, Pennsylvania. And with me is the warning coordination meteorologist, Jonathan Guzman. So go ahead, Jonathan.
Hi. Just going to say hi, everybody. Thanks for joining. And I saw Troy Wilrick. I just wanted to say hi to. I remember working with him when I was down in Melbourne. So good to have those on from down south in Florida, along with all the rest of you from Ohio. See ya, Youngstown, and several Pennsylvanians. So good to have you guys on board this morning.
Yeah, thank you everyone for joining and tuning in today. Hopefully you get something out of this webinar. We're really excited to present it to you. And today we're going to be talking about radar basics. So this is not an advanced radar course, but we will be talking about some interesting things you see on radar, how to interpret what you're seeing, to also see what it looks like in the sky if you're outside looking at clouds, what it is that you're seeing there, and then the hazards you can expect. And then also some advanced applications. So if you're really curious about interesting things like tornadic debris signatures or hail spikes, we're going to be going into that too. So with that, we shall start with a brief introduction of who we are. So we are the National Weather Service in State College. This is our office. If you ever wanted to come visit, we are on the 3rd floor. We are comprised of 14 forecasters, 6 electronic technicians, 1 hydrologist, 1 science and operations officer, 1 observing program leader, 1 warning coordination meteorologist, which is Jonathan with me today, and 1 administrative assistant and 1 meteorologist in charge, who is our boss, essentially. We are open 24/7, 365. So we are always there, no matter what time of day, no matter holidays. We're always providing forecasts and warnings, as well as maintaining any of the equipment like Doppler radar, which we're going to be talking about today, and then all the other observation systems. So if you ever have a question about what's going on around you, or the forecast or anything, and you call us, we will answer because we're always there. So if you ever wanted to talk to a forecaster, we will always be there to answer the phone for you. So if you were curious about how to find us online, we're on social media. We have Instagram now, which is new. So we're at NWS State College pretty much for Instagram, Twitter, Facebook, YouTube, and then of course for the forecasts and our main homepage for weather.gov/CTP. We serve central Pennsylvania. So this yellow outline here is the counties and area of Pennsylvania that State College specifically services. If you're interested in forecasts for other parts of Pennsylvania, you may have to go to the Cleveland, Ohio forecast office, Pittsburgh, Binghamton, New York, or Mount Holly, New Jersey. So those different offices will service those different parts of Pennsylvania, but we are focusing on central Pennsylvania. But no matter where you're tuning in from today, if you want to use this training to take back with you home, if you're not in Pennsylvania, or if you're in a different part of Pennsylvania that's not central Pennsylvania, this is transferable everywhere. So don't worry about, I'm not in central Pennsylvania, I don't know if this will count. It will count, don't worry about that. So I'm just happy to have you on board and learning about radar with us. All right, and with that, I will pass it over to Jonathan to talk about radar and how does it work.
Thanks, Rachel. So yeah, we're going to start off with kind of the very basics, how a radar, actually a lot of people think that a radar is constantly pulsing out energy, which it is, but it spends the majority of the time, really about 99% of the time, actually listening back. So we'll go ahead and kind of show you some visuals of what that looks like here. So starting off, and this is again applicable anywhere you're at. So our radar north of the office in State College, close to University Park Airport. They look like this. A pedestal, usually 3 to 4. Some are actually probably 5 stories now. And then you see the white thing that looks like a soccer ball sitting in the sky. So that's the radome. That's all the protective housing for the radar. So inside's actually, is on the last slide there, is actually a rotating antenna, a dish that scans, starts at 1/2 degree off the horizon, scans around, tilts up, scans around again, and then goes up to about 19.5 degrees off the horizon, and then it comes back down and does it again. And depending what mode we have the radar in, can fluctuate how many of those lower level scans we get versus basically just going up, stair-stepping up and coming back down. But to show you the visual, what it looks like here. So pretend on say a sunny day where we start to get afternoon cumulus clouds type building here, and then we get showers and thunderstorms to develop from that. So you see the radar beam, it actually pulses out there with time, and then depending on what it hits, the targets that it hits, so it can be, as we'll get into here in a little bit, mostly talking about rain, and that today it can also pick up clouds, snow, any precipitation, but insects, anything that it hits, it's going to measure that reflective power off of that as the beam goes out and comes back to the radar and listens. So depending exactly what it hits and how much of whatever it hits is going to show that return. So as what you're used to seeing likely on your radar apps or on TV, the cooler colors, the blues and greens, are going to be the lighter returns, or the weaker returns, if you will. And then as we get into the warmer colors, the reds, purples, that's going to be the higher returns, or the higher reflectivity that the radar is actually picking up here. So as this slide kind of suggests here, you see that beam start to propagate out as it goes out toward the radar, or away from the radar, excuse me, out toward the target. So in this case, we may have birds, whatnot flying out in the sky in the atmosphere. So that beam hits that, and then that measured reflected power works its way back to the radar here. And then that's the readout that you see when you look at a reflectivity image. So kind of showing it in a little faster motion here. Imagine we've got a raindrop there off to the right, and then the radar dish to the left. So it sends that beam out, and of course we're going to have, in a scenario where it's raining, you've got several millions of drops that radar beam's hitting. We'll talk about it a little more, but as a radar beam actually goes out in the horizon and spreads out, the beam widens, so it's going to catch more targets as it goes out and hits those. So it spreads out and becomes wider with distance. So in this case, we see it hit this raindrop, but that beam, notice when it hits that power doesn't all just come back to the radar. Most of it gets reflected, scattered in all directions across the atmosphere. So we're not going to see all the measured power necessarily come back toward the radar. A lot of it's propagating in all different directions. So say in a case where we've got precipitation happening, that radar beam's going to go out, not each individual drop, but hit several of those droplets, millions of those droplets, and then scatter and spread out in all directions. And then a good chunk of that energy will still come back toward the radar and allow us to measure the reflectivity, the amount of a target that it's hitting. So, and we'll talk about here in a little bit too, but the reflectivity we see come back toward the radar is a measure of both the number of droplets it's hitting, and then also the size of the droplets it's hitting. So both of those factor heavily into it. And really it's the size that ends up being a factor in increasing the reflectivity or not. So the size or diameter of the target or drops that the radar beam's hitting is going to have a heavier influence on the reflectivity amounts that come back to the radar. So starting, one of the limitations, as I mentioned, imagine our radar sight right here to the left of the image, the bottom left. So as that radar beam we talked about, you see how as it goes out in distance away from the radar site, how it spreads out and widens. So that's good in terms that we can actually sample and see more targets, measure more targets, hit more things as we get further out. But you're also we lower our resolution. So you can imagine the beam goes out, spreads and widens. You're kind of, you're taking out some of the finer detail that you would if the beam was narrower in width, if you will. And that gets a little more into when we talk about the velocity part of the radar later on in rotation, say as with mesocyclones and tornadoes. But for now, on the reflectivity side, again, we're going to widen. You're going to hit more at that point as you go further out, but you're going to lose again some of that detail. You're going to take in a bigger average of the area that the beam's hitting. So the limitation this is really touching on here is we get further out from the radar site. So due to the natural curvature of the Earth, with the Earth being round, the beam actually shoots higher and higher in the atmosphere as we get out and away from the radar. So even at this lowest sampling of the radar, the half-degree elevation off the horizon. And there are some radars that are starting to test. I think Cleveland, for example, is one of our closer ones. Lower elevation cuts, say I think 0.3 or 0.4 degrees. But for now, our radar at University Park or a University Park State College radar starts off at half degrees, the lowest we get. But so even that scan there, that lowest scan, as we get, say, a storm 80, 100 miles or certainly more than that away. So for us in our periphery in central Pennsylvania, we get into Lancaster counties, Lebanon counties, Warren, Somerset, it really starts to increase in elevation where we can't see much below, in some cases, 8 or 10,000 feet. So it's something we certainly have to take into account. We're very, very glad and appreciative of all spotters we've got that really help us understand what's happening down in the low levels beneath that radar beam. We can certainly infer what's happening below from what's happening, say, in the mid or upper levels of a particular storm. But having the ground truth's really key in that instance, with not having the remote sensing capability to see exactly what's going on closer to the ground. So it's just with this closer storm in this example, where maybe we can actually shoot and see that at 3,000 feet and all the way up as the radar beam tilts up. So certainly a limitation as we get further out from the radar beam. As I touched on here a few minutes ago in terms of what reflectivity actually is. Again, this is the portion of the radar output that you're going to see most often is the reflectivity. So an example image there from the State College radar on the left of the screen. So not a lot to pick up on here. The very cool colors, even some of the whites, really not measuring any reflectivity in the atmosphere on this particular scan. So again, we're talking about the return power. So as the radar pulses out and then spends most of its time listening back, this is the output that we'd see maybe on a day like today, where we're not going to see much, if anything, on the radar. So the intensity of what it's hitting, so again, the amount that it's hitting and then the size of what it's hitting factors into the reflectivity portion of the image. And then the units, if you ever see these, if you're looking at an app, I'm sure most of them say on there dBz. So that's essentially the scale or units that we use to measure reflectivity. So to give you an idea there, if you get into the negatives, you're not really picking up on anything. Radar's not seeing anything other than maybe some moisture or some high clouds. In particular cases, you start getting into the 60s, you're getting some pretty heavy rain. 70s, you're likely mixing in some hail. And then if you get to the upper echelon there, if you get into that 80 range, it's, I don't know if torrential is a fair enough word for the rainfall that'd be falling at that point, or the hail that would be likely involved in that at that particular scale there. And then the idea of the scale, so starting off again here, the weaker returns, so those negatives kind of in the whites and light purples there, if you will. And then as you get into the light blues, this is where we could start to see some light rain or maybe drizzle. We had that on a few, I think this late, maybe last Friday, we had some drizzle around behind the frontal boundary there. And then into the greens, you start to get a little heavier, where it's noticeable. You go out, you're going to get wet. Worth noting too, in the wintertime, due to the nature and that of snowflakes not being near as big in diameter as raindrops are flatter in appearance, we're not going to see as high reflectivity from snow as we would from rain. So snow, typically you max out if you get into the yellows. So say in this case 40 dBz, that's pretty heavy snow. But getting into the yellows and reds, we're getting into a pretty moderate to maybe at times heavy rain if we get into that red. And then again, the 60 and up dBz values are the torrential, the heavy downpours that if they sit over you, you're going to start seeing high water and flooding issues, and likely hail in a stronger thunderstorm. So to kind of generally characterize the scale here, so the extremely light, and then you see the moderates there in the yellows, and then you get up into the purples there, and it's pretty heavy. So shifting the spectrum here. So we talked about reflectivity, which again is what the targets are hitting. So the amount of what it's hitting, and then the size of what it's hitting. So then the other aspect we really focus in on, especially in terms of warning operations, is looking at velocity data. So this is all, again, the same idea, the radar beam's pulsing out and then listening back. But now we're looking at the direction that the particles that the radar beam's hitting are moving. So the greens here on this image would be all particles moving inward toward the radar. So in this case, they're moving from southwest to northeast, so moving in toward the radar site. So the radar site's right here. So you have to know right where that's at to read the velocity data. And then conversely, up to the northeast of the radar site, you see the reds, which are indicative of particles and precipitation, what have you, whatever the radar's hitting, moving away from the radar. So again, in this case, southwest and northeast. So obviously on this day, a good southwesterly flow, winds out of the southwest. And the radial velocity, you see here that wording. So again, basically talking the radial of the radar, we're seeing that the zeros in terms of anything being picked up on the velocity scales right through here, this real light white here. So anything that's perpendicular to the radar beam is going to read 0, because again, it's got to measure the particles moving toward it or away from it. So you see in this case, everything kind of moving right at the radar, all the greens and then the reds all moving away. And then everything, essentially in this case, it's perpendicular with the white here. We're not going to measure anything. So that's another, if you will, limitation with radar, as you get particles that aren't moving directly toward or away from it. You're going to measure lower wind speeds at that point. All right. So as I mentioned there, the perpendicular particles, you're not going to be able to measure a true wind speed from that. So again, you see this is then this scales in meters per second too, mind you, just for unit purposes. But in this case, moving, so you got your radar site here in the middle. So the blues would be inbound, so westerly wind in this case, and the reds outbound. So our winds would be west in this particular example. And then again, as we're perpendicular, you see how we're not measuring anything at that particular point. All right, so moving on. So that gives you some of the basics in terms of reflectivity and velocity. Again, the two real base moments, as they're called, or base outputs of the radar that we really focus on. So now we're going to move into looking at what we would see in terms of some of these radar signatures, and then applying them to what you would see out in the field if you were looking at, say, a shower or a thunderstorm that was occurring. So just a general review, and if any of you have taken our spotter training, which I know several of you have, this will be a somewhat review for you there. So in terms of thunderstorm types, I'll back up here. So ordinary single cell. So that's what we see a lot of on any given day. That's a majority of our storms. So the pulse type, we see the billowing, upward rising motion with all the instability in the atmosphere. You see the puffy cumulus clouds ascend in the sky, and then eventually they come back down. So say 20 to 30-minute life cycles, and then they're over. Usually no severe weather with those, maybe a brief heavy downpour. And then the multi-cell type clusters. So those are going to live on a little longer. It could be several of the pulse type storms right against each other. Could be a squall line of thunderstorms, so say along a cold front moving through, or again, the several storms lined up right against each other, maybe a larger complex of storms that lives over several hundred miles and propagates westward across Pennsylvania. And then supercells are the ones, the textbooks that you see a lot of in terms of severe weather. They're long-lived, certainly going to have severe winds out of most, if not all of them, large hail, and then those are your best threat for seeing tornadoes develop out of on any given day. So applying radar signatures to each of these to give you a general idea of what that would look like. So reviewing here the ordinary pulse type thunderstorm, the life cycle. So again, you got the towering cumulus, so all that warm, moist air ascending throughout the atmosphere. Then it becomes mature there. You see in the middle image where you still got that warm rising motion ascending. And then you're also starting to get the downdrafts, all that cool, moist air descending when you get you start to get into the precipitation core. And then the dissipation stage, again, 20 to 30 minutes, where you see we're all downdraft now. So it's all cool, moist air descending, and no more instability left over for additional thunderstorm development, at least in that particular area or from that particular storm. So an example here of a loop of what this would look like on radar. So we're looking at reflectivity here. So you see these individual little storms popping up with time as it starts here. I'm not sure the lag coming over everyone's internet, but you can kind of get the general idea. And there's a, to help you out with reference here, there's a timestamp on the radar image, and we paused it longer after that last image. So you see these storms come up, you see some of the red, the higher reflectivities, so say pushing 50, 55, maybe even times 60 dBz. And then you see like this particular storm, it quickly dissipates, and you lose all reflectivity at the end here as it goes on. So again, 20, 30 minutes throughout its life cycle and it's done. So you see these storms, they look impressive on radar, but then they quickly fizzle out. And then depending on interactions, so you see kind of, just as a little added tidbit here, you can see around this, you see this little ring that spreads out in the clearing around this storm. So this is an outflow boundary actually spreading out in all directions in this case. So helping to fuel this storm up to the north here in this particular case. And then that storm would likely, once it loses its luster and instability and lift from this boundary off this storm, it would fizzle out. And you may be one of those days where you see storms creep north for hours. So again, the rain-cooled air hits the ground, kills off the storm. It's the cooler, more stable air undercuts the storm that had been mature at that point several minutes ago. But then, of course, you get that lift from this storm in this case, and then that helps to serve as lift and focus for additional development there. So it may kind of look like popcorn at times too, with storms just kind of popping and then fizzling out. Yeah, I jumped the gun. Rachel actually put this, Rachel and Quinn, I know our student, pathway student this year that worked hard on this presentation, actually denoted that in here for you, the outer radius of that band there from that outflow boundary. And then looking off in the distance, so you see the towering cumulus here. You can start to see maybe trying to get an anvil. So again, the upper levels of the storm spreading out as it gets into that stable layer of atmosphere aloft called the stratosphere. So may look like a fairly strong storm looking out at it, but again, there's no wind shear in the atmosphere to help it to organize, so it's going to quickly rain itself out. Again, impressive for a short period there, but then quickly fizzles. So ordinary cells, again, still showing that loop here for you. But in terms of hazards, downburst winds are going to be the main threat with these. If you do see that, just when they rain themselves out, all that cool, moist air rushing downward toward the ground and spreading out. So certainly could get some minor, especially tree damage out of those, just depending exactly how strong and where they occur. Rain, the saving grace with that, normally it's not a long-lived type event in these type of pulse storms with heavy rain, maybe a real quick 5-10 minutes type thing. So if you're driving, that's really one of the bigger nuances of trying to see through it. But again, typically not severe, just due to the lack of organization and time for lift and ascension through the atmosphere there. So moving on here, upping the scale a little bit to the multi-cell type thunderstorms. So again, these can take on several varying forms. So in this case, really more of a, if you get the towering cumulus, so the initial growth stage of a thunderstorm, and then the mature stage lined up next to it, so say a storm that's got, again, both that updraft and downdraft, coincidentally in present at that point, and then the storm, say in the dissipating stage, wrapping up on the downdraft stage. This may go on, it may sound like you have a thunderstorm going on right over you for hours, just depending on how many of these develop. So you can also get them, so say back building into a larger scale complex that happens. You see a lot of those out on the Great Plains as you get into the later spring and summer months. And then we'll talk about lines here in a little bit. So depending on the upper level winds here, so if they're stronger, kind of blowing in a direction that the storms are moving, you may just basically see the new cells develop on top of each other, carrying cells downstream with time as they move. So say maybe west to east in this particular example. And then if you get these upper level winds actually being stronger in the opposite direction, that's when you can start to get the back building, some storms sitting over the same spot for multiple hours on end, and really where you start to see the flooding issues from the training type storms at that point. So in the complexes we alluded to there, if you start to see that back building in the larger scale complex of storms, the fancy type of terminology for that, you may hear MCS, stands for mesoscale convective system, or mesoscale convective complex, MCC. So if you ever hear one of those, are usually duration, say several hours or maybe all night, they survive and then they propagate east. Usually again in the night, there would be out in the plains and then get to us the next, say morning or maybe early afternoon type thing. So if you do start to see one of those, that's the terminology there. And then if you get more of the linear, so say a line of storms along a cold front, as we typically get a lot more of here in this part of the country, we would refer to that as a squall line. It's still a MCS or mesoscale convective system. It's just more of it's a specialized type, if you will, in terms of a line there, instead of maybe a more circular or a larger complex type look. So this is an example of what one of those squall lines would look like. I mentioned we get a lot more of these. So you see the development, maybe there was a larger complex that came out of the upper Midwest earlier in this particular example. It was started again as we get into Northwest PA. See, not really a lot of organization, and then as it races south into the central part of the Commonwealth here, it starts to organize more into this line, and then really bows out and stays together as it gets down toward the Piedmont and Philly and off the New Jersey coast into the Atlantic there. So again, a very typical type of spring or summer type evolution here in Pennsylvania for us to see. And as we say linear, it looks like a line, so fairly easy to pick out if you can imagine them there on the radar. And then what it would look like if you were actually out observing or spotting. So if you've heard the shelf cloud terminology, we focus a lot on spotter training on. So it looks very, very ominous as it moves at you. But the main thing to remember with these is they're detached from the thunderstorm base. So you're not, in most cases, the main threat with these is going to be high winds immediately under and behind them. So what's happening here is all that cold, moist air that is descending, so all the downdraft is rushing downward toward the ground and then spreading out in the direction that the storm's moving. So that's why you kind of get this fragmented edging and kind of protruding outward at you. So in this case, would be moving somewhat left to right, if you will, in this image. And then right underneath and behind it's where, again, all that downdraft is pushing that cloud edge out. So that's where you're going to get into the heavy rain. And we'll talk hazards here in a minute, but they can produce tornadoes, but they're typically weaker and short-lived and not going to happen in most cases. So the damaging winds moving in the direction that the shelf cloud's moving, or the squall line is going to be the main threat. Flooding typically not a huge issue, just due to them usually moving in a pretty good clip. But if you get multiple of them or they move slower, it can become an issue. And then hail and tornadoes usually on the smaller or weaker end with these. All right, and finally, supercells here. So textbook example, a perfect one would look like. So the main thing to focus in on, without really getting out of the scope of the radar presentation here and putting in on too many of the details of this, between this updraft and downdraft interface, you see the lowering of the wall cloud. You start to see that rotate. That's where you need to look for the tornado developing. So usually in that interface there, and especially with the rotating wall cloud. And the wall cloud versus the shelf cloud we'll touch on here too. But remember, that's attached to the thunderstorm, to the base there. And when you start to exhibit the rotation, that's what you really need to focus on. So certainly updrafts 100 miles an hour or more with these. So very vigorous, rising, moist, unstable air throughout the atmosphere. So if we're going to see the stronger type tornadoes, they're going to come from these supercells versus the other two types we looked at, the multicells and pulse type storms. So downdrafts, essentially winds, instead of rotating like a tornado would, we can get, again, the downdrafts, so all the rain cooled air rushing downward to the ground, spreading out. So outflow winds, we've seen damage with these well in excess of 100 miles an hour. And then I alluded to a little bit earlier, the cause for these, the vertical wind shear we talked about. So you've got the winds actually turning with height throughout the atmosphere. So we call it veering. So they're actually turning, so maybe south or southeast down at this ground. And then as you work up through the atmosphere, they start to go clockwise. So more southwesterly and then westerly, and maybe even northwesterly aloft, several tens of thousands of feet up in the atmosphere. So we start to get that. We have better organization of that updraft and downdraft and that interface between them, and really allows for the storm to evolve and sustain itself and make for higher probability of severe weather down the line. Okay. There we go. So getting on the radar image of what one of these would look like. So the supercells, again, this is looking reflectivity. So starting off with our updraft. So again, these, you got the vertical wind shear, the organization of the storm. So essentially where this rain-free area is, or the very, very weak return, that's going to be where the updraft's located. And then immediately adjacent to that, it's going to be where all the downdrafts, so all the precipitation is. So you see closer to this updraft core, where all that warm, moist air is going up, you've got these purples, so 70, 75 dBz returns, indicative of extremely heavy rain, likely large to giant hail in some cases. But again, it's separate from that updraft, so the storm is going to be able to sustain itself, just immediately adjacent to it. And then you get further downstream from that, from the core where the heavier precipitation is going to be. And then you see the colors generally drop off as you get from kind of going southwest to northeast in this case, with the lighter rain and the downdraft out further downstream here. So the really key feature of a supercell, we're going to see potential tornadic development. So around this updraft here, again, we've got the wind shear, so counterclockwise turning of the storm with time. And you start to see this little, what we call hook echo, or hook develop around that updraft. So the updraft's here, you've got the counterclockwise winds, the rotation going on. So it's actually the updraft's pulling this reflectivity, so this precipitation, this rain and hail around its backside there, producing that hook echo on the reflectivity. So that's the reason why you can see it like you do. In most cases, typically, if you're going to get a tornado, it's going to be right about in the base of this hook here. In this case, there may be high enough reflectivity where we may actually be able to see debris out of it. And Rachel will touch a little more on tornadic debris signatures and some other radar fields we can look at to assess that a little further. So that's essentially what's going on in this case. So looking out at it in real time, you've got the wall cloud again attached to the thunderstorm base. So this think lowering here between that the new development, the updraft and the downdraft, you can actually see part off here to the right of this image. So you start to see this rotate typically counterclockwise. That's really where you need to watch for that tornadic development later on. So supercells, again, winds, hail, tornadoes, flooding, heavy rains, all fair game with these, and we're going to see the highest probability of any of those in most cases out of supercell type thunderstorms. So a quick review here on the couple of the keys we've talked about. So the MCSs, mesoscale convective systems, again, a type of multi-cell thunderstorm. You start to see this type feature coming at you, this protrusion of a cloud, looks like a straight line of clouds, maybe with real ragged fragments moving at you. So the shelf cloud, you're looking more the wind punch right behind it, as that shelf cloud passes over you and then behind you, and the heavy rain with it, and again, small hail. Tornadoes, weak tornadoes are possible with them, but the greatest concern is certainly the straight surge and punch of winds from behind it, and the heavy rain along with it. And then supercells, wall clouds. So I know they can be hard to see out in the field at times, and we go over these a lot more in our spotter training course. But again, instead of being detached like the shelf cloud, the wall cloud's attached, the thunderstorm cloud base, and you would really look for the vertical rotation with this. So again, typically counterclockwise. You start to see that where the shelf cloud, you may see a little, it may look like rotation, but it's likely doing it instead of vertically, it's more of a horizontal nature, if at all. But again, normally you're not going to see that with a shelf cloud. You're just going to see a cloud fragment racing out toward you, maybe lowering with time, but no real distinct rotation. The wall cloud's got the vertical rotation with it, and subsequently the greater threat of large hail, strong, let's say 100+ mile an hour downburst winds, and then tornadoes with it too. Then a few more examples here looking on radar. So the mesoscale convective system, you see what looks like a pretty good cluster. A lot of rain really behind this initial edge. And usually the leading edge of these has got the heaviest rain associated with it, just due to the more unstable air where the system or the line's moving into. There we go. So yeah, this line here, that's much of rain and right punch. And again, the shelf cloud you would see out in the field moving at you. And then the supercells, again, these brighter, real warm colors where you've got the larger particles, the larger hail and rain. And then the smaller particles, as they get away from the updraft there, tend to be able to spread further downstream there, away from it. And then this hook echo, again, indicative of a rotation occurring in the storm right around the updraft base here. And then our wall cloud, again, looking vertical rotation. It's always the key component of those. All right, so I'm gonna go ahead and let Rachel get into more of the advanced topics and what we call the dual polarization part of radar too.
Thanks, Jonathan. All right, so I know there are some questions coming in, so Jonathan might be answering those as I go through. There was one question about velocity that I can answer right now. So for radar reflectivity, the radar sends out a pulse and listens for the pulse to come back. And when it does, it records what is happening with whatever particle that it hit. It can hit clear air, it can hit bugs, rain, hail, and then it records what it is it's doing. Is it moving towards the radar? Is it moving away? But that is all that it can record for velocity. So when a radar sends out a pulse and listens back for the pulse to come back to its radar, it only tells us if the particle is moving towards the radar or away from the radar. Nothing about the vertical. So when we look at radar velocity, we really have to be able to kind of build a 3D picture of what's happening by looking at all those different radar scans to be able to see what's falling, maybe how fast is it falling, and then also looking at those scans on the horizontal plane. Are particles moving away from the radar? Are they coming towards? Based on that, can we see anything interesting like a wind shift or rotation or convergence or divergence? Those are some of the things that I'll talk about here. And before we get into advanced applications, I have one quick little aside that I'd like to talk about. So if anybody's seen that episode of Mythbusters where they try to cook a chicken with radar, sorry to burst everyone's bubble, but they did that episode incorrectly. They didn't actually understand completely how radar works. So radar isn't constantly sending out pulses like infinitely fast all the time. If it was, you could cook a chicken with a radar. So if it was constantly sending out pulses, you could actually like cook a chicken. That would be like a microwave. You would put food in the microwave. It's constantly sending out pulses infinitesimally fast, and it's cooking your food. But with radars, they send out a pulse, and then they wait, and they're listening, they're listening, they're listening, and then the pulse comes back. So because there's that waiting period, they spend 50% of that time waiting for the pulse to come back. You don't actually like cook food with a radar. So it's not actually that dangerous to be like super close to a radar. But that being said, it is sending out microwave radiation. So you don't want to be standing next to a radar for prolonged periods of time. So if you ever were to go visit a radar, or if Doppler on wheels were to come to your town and you wanted to go talk to the scientists there, you don't want to be next to the radar because for a long period of time, because that will be dangerous for you. You don't want to be constantly being hit by radiation, but you won't be cooked. So just a fun little aside with that. And now we can get into some advanced radar applications. All right, so the first thing that we're going to talk about is hail detection. So sometimes with supercell thunderstorms or other thunderstorms that are producing a lot of hail, you'll get this funky little spike on the backside of a storm. So that's this little spike here, and we're looking at reflectivity for this image. You can see that there's really high reflectivities. Remember, Jonathan told us that anything above like 55, when we get into those pinks, is pretty much indicative that hail is occurring. So we can see that there's 76 dBz here. That's pretty high. So we can say, okay, there's hail. What is happening? And then all of a sudden we get this weird spike. So this spike is actually not part of the storm. That's not anything going on with the storm. You're actually seeing something interesting happening based on the hail that's in this hail core. So let me go back here. I have a 3D printed hailstone to try to demonstrate what is happening with these three-body scattering signatures, or hail spikes. So this is my hailstone. It's in the core, and radar beam is coming, and it hits this hailstone. So when it hits this hailstone, remember, radiation spreads out in all directions, including going back to the radar. So when the radiation hits this hailstone, spreads out in all directions. And one of those directions happens to be down towards the ground. So when we have our hailstone that's hit by the radar beam, then the beam gets deflected towards the ground because there's just so much hail, or the hail is really large, that beam now goes towards the ground. Well, the ground also absorbs that radiation and releases it back, and it brings it back up to the hailstone, and then that sends it back to the radar. So there's a three-process, like a three-body process happening here, which is why it's called three-body scattering signature, TBSS, or hail spike. And that's because it's hitting the hail, hitting the ground, hitting the hail, and then going back to the radar. So what we're actually seeing here in this hail spike is the ground. So we're not actually seeing the hail core. We're not seeing anything happening with the storm. We're actually seeing ground right here. So this is the reflectivity of the ground, the grass, whatever is on the ground. So that's a really interesting thing about these hail spikes. So you can see them when we have a storm that's producing really large hail. For example, this kind of stone is really large. Or it can happen when we have a hail core that's producing millions and millions of really itty-bitty small hailstones, so like pea-sized. So when there's a hail core, if it's really dense with small hailstones, or if we have some really large hailstones like this, we can get a hail spike. So you can't actually determine what size necessarily hail you're going to see when you see these hail spikes, but you can say with confidence that there's hail happening in this storm. So if you're ever curious about that, that is what's happening in the reflectivity image. So next, reflectivity can also show us some really cool non-meteorological scatterers, so things that are not storms. So for this, we look at reflectivity, and then also we look at something called the correlation coefficient. We'll get into more detail in that in a little bit. But as we can see, we have our radar here at the center. That's our little black circle there, and State College is labeled. Some of the other cities are labeled. And we can quite clearly see, labeled by 1 and 2, things that look like storms, right? So that is kind of our classic pop-up thunderstorms, popcorn convection. But then we see all this other junk around the radar that's not a storm. You know, it's not constantly raining in this weird circle pattern all the time. and that is actually our non-meteorological scatterers. So the radar can pick up on a bunch of different things. It can pick up, of course, on our storms, which are very important and care about, but it's also picking up on all the ground clutter. So trees, buildings, bugs. In fact, if you are a really avid radar watcher, if you look at radar around sunset and you have a loop of radar and you're looking at probably like maybe an hour's worth of radar around sunset, you'll see that the circle around the radar expands. Now, think about why that might be. The radar around, or the circle around the radar, will expand because all of the bugs are coming out at night. So sometimes all of this can be bugs. And then also, if you're looking at a radar map of the entire US and you want to look at it through the months, like a diurnal cycle of day and night, and then through the months, you'll actually see all the bugs kind of migrate across the US, which is really cool. So radar can actually pick up a lot of neat things. The next neat thing that it can pick up are forest fires and wildfires. So this is actually picking up on smoke from a wildfire. And you can see that here, and it looks not like a storm because it's coming from one central location. You can kind of see the origin point of where it's going, and it's all being advected kind of in the same direction here. So that's a kind of clue to yourself that this is not a storm, because it's all kind of originating from the same point. So you kind of have to be a detective sometimes when you're looking at radar to really figure out what might be going on. So we actually call this pyrocumulonimbus. So forest fires can actually spawn cumulonimbus clouds from all the heat and influx of all of that energy into the atmosphere. So from the smoke, we can actually get pyrocumulonimbus, which is what's happening over here. Because this is a higher returns, higher reflectivity, we actually get our thunderstorm that's occurring because of all the smoke and pyrocumulonimbus activity and heat that's happening at the origin point of the thunderstorm, or sorry, the forest fire there. All right, so now let's take a deep dive into velocity. So Jonathan showed you kind of an easy example of velocity where we just had reds and greens going towards or away from the radar. This is the same kind of concept, except now we're in colorblind friendly territory. So if you have an issue between distinguishing red and greens, this is supposed to be a little bit more easy to distinguish between the blues and the reds. So blues are going towards the radar and reds are going away from the radar. So blue is negative because we have the velocity going towards the radar, and then the positive velocities, or the reds, are particles moving away. So remember that at the surface, or at close to the radar, we're measuring particles that are very close to the surface. And remember, as that beam goes out away from the radar, it gets lofted higher and higher into the atmosphere. So as we get further and further away from the radar, we're actually seeing the mid and upper levels of the atmosphere. We're not seeing the surface anymore. So you have to be very careful about what you're looking at, because when you're far away from the radar, that's not representative of what is actually at the surface. So the further away you get, you have to kind of remember that you're not looking at the surface anymore. You're looking at mid and upper levels of the atmosphere. So this is where it gets a little bit tricky. So now we have an interesting velocity pattern where at the surface, we have a south wind. We can see blues and reds going, blues going into the radar from the south, reds going away from the radar towards the north. So at the surface, we have a south wind. But at the very, very upper levels of the atmosphere, if we go all the way out to this outer ring, we can see our blues out here are pointing from west to east, and then our oranges or reds are pointing from west to east again. So that's telling us that we have a west wind at the upper levels, and we can kind of see with this wind barb map with height that that's what's happening. So at the surface we have our south wind, and as we go up in the atmosphere it shifts to a west wind. So just know that if you're looking at velocity, you can actually see some really cool things happening at the vertical levels of the atmosphere, and also you can see some really cool things happening at the surface as well. So for example, I'm going to take a sip of water here, sorry. If a front is coming through, we can actually see that wind shift. So we know that when fronts come through, they bring with them a wind shift or shift in the wind direction. Maybe sometimes it's faster or slower winds. And also, we can see that on our velocity. So when we look at our velocity image here, there's a lot of funky things going on. At the surface, we have our blues and our reds showing us that wind is coming from the southwest and going towards the northeast. So we have a southwest wind at the surface. But then above that, now all of a sudden we have a northwest wind coming in, and it's colliding with this southwest wind that's at the surface. So when we look at the upper levels of the atmosphere, we can see this front coming through, telling us that we have a northwest wind coming in and going to like override the southwest wind. So a little bit complicated, a little bit hard to wrap our head around. So we're going to, take it slow here with the velocity examples, but just showing you that you can see some really interesting things on radar, especially when we have fronts coming through. I've seen this plenty of times just with the Pennsylvania radar when we have fronts in the fall and winter time. Classic, almost to a T, this picture right here. I know this is very idealized. We can actually see this pretty well when we do have fronts moving in through the region. So next time there's a front coming through, check your radar and see if you can actually find it on the radar image. All right, so now we're going to move into some more interesting velocity applications. Are we looking at straight line winds or a tornado? Everyone's always interested in finding that tornado on radar. Can we find the rotation? So red next to green or orange next to blue would imply that there's a wind shift, right? Because we just looked at the previous example that different colors means different directions for the wind. So if we're looking at red touching green, which is the classic radar color scheme, if you have a radar app on your phone or if you're looking at it online, red touching green is kind of the classic, there's a wind shift. Now, what's very important is being able to know where the radar is relative to the red touching green. Because red touching green doesn't necessarily mean rotation all the time. The relative location to the radar matters a lot. So remember, your radar is at the center of your image, and everything is relative towards that because you have your radar at the center and it's sending out signals in a circle around the radar. So we have to know where our radar location is to be able to determine the direction of the wind. So for this example, on the right here, I cannot pause the video, so I apologize for that. Our radar is down towards the bottom left corner. So that is where our radar is. And because that is where it is, we see reds going away from the radar on the right side of this image here, and then greens coming towards the radar on the left side. So because we have red going away and green coming towards, that is actually rotation because it's relative to the radar location. So the next image here on the left is actually a downburst image. So we have red touching green. It's a little bit hard to see because it's not as great resolution, but similar kind of scenario here where we have red touching green. Oh my goodness, red touching green means rotation, right? Well, not in this case because our radar location is here, and if we follow that, take one beam or one slice of the radar data and follow it from the radar location to our area of interest, we can see we cross both green and red. So green means, remember, going towards the radar, red is going away. And because we cross along one segment, both of these, we can see green going towards, red going away. It's a downburst. We have diverging winds here. It's not rotation. You really need to be able to place your rotation that you're looking at or suspected rotation to where the radar is to be able to actually determine if it is rotation or if you're just looking at a downburst. Conversely, if you were looking at this and the colors were flip-flopped, you might actually see convergence. So if you had red and then green, red going away from the radar and then green going towards, you would have convergence. So this is a really good tool to be able to determine, okay, am I actually going to get a tornado here, or are we just getting really, really strong downburst winds? So radar can be used for a lot of different tools. Deciphering rotation and a tornado threat is one of them for sure. So let's look at this example again and decipher a little bit more now with a slow single image, a little bit easier to see. So we have our reflectivity on the left and our velocity on the right. Radar location again is down towards the bottom left. It's a much different picture than your downburst winds. So we have our reds going away from the radar, greens going towards. And because they're not along the same beam, the same radial from the radar, it's kind of like across several beams, that is how we determine if there's rotation. So we can actually see counterclockwise rotation here. Good rule of thumb is using the right hand rule when you're looking at this. So you put your hand in line with the direction of the winds, curl your fingers towards the other direction that the winds are going, and your thumb tells you if there's rising motion or sinking motion. So we can see counterclockwise rotation. Generally, that means rising motion. When we have rising motion, we have thunderstorms and tornadoes. So this is actually telling us that we do have rotation. It doesn't necessarily mean there is a tornado at that instant right now, but that does mean that we do see rotation and probably the potential for this storm to produce a tornado. So with that, we're going to move into dual polarization radar. This is opening our toolbox now, because before we were looking at single polarization radar with just one beam going through, but now we have an additional beam. So we have our horizontal beam that goes through the atmosphere to collect all this data, sends it back to us. Then we added a vertical beam that also is going to go through the atmosphere, collect all that data and send it back to us. But because we have two different orientations of the beam, we can get a lot of different ideas on shapes, orientations, different objects in the atmosphere, and the list goes on and on. So we're going to look at a few of those right now. So with the advent of dual polarization radar, our first thing that we have been able to look at is differential reflectivity. This tells us about the shapes in the atmosphere. So if you're ever looking at differential reflectivity, or ZDR as it's sometimes called, that's telling us about shapes. Correlation coefficient, which is also super popular, it's always kind of this pink and yellow image. That's telling us about the diversity of the particles in your scanning volume. So that's telling us about shapes, orientations, composition, like is it made out of ice, is it made out of water, is it made out of wood, if it's debris, etc. So differential reflectivity, only about shapes. Correlation coefficient is telling us how diverse are those particles. Are they all the same? If it's all rain, it will tell us we're all looking at the same thing here. If we have rain and hail, or hail and tornadic debris, that's also going to tell us, we have a diversity of shapes and particles in the scattering volume. And then finally, specific differential phase, or KDP, tells us about the non-spherical stuff that's out there. So non-spherical stuff meaning weird shaped hailstones or raindrops that are really, really large, because believe it or not, raindrops, when they are large, they actually flatten out. And I have an example here, and become kind of like a French roll shape. So raindrops that are really large have the flat bottom and kind of a slightly rounded top. So they are not spherical, and they're not any other shape but this guy here. So when raindrops get fat, they become non-spherical and flatten out, and then our specific differential phase kind of lights up here and tells us that. So first, let's look at ZDR. So what shape is out there? Remember, differential reflectivity ZDR is telling us about the shape. So spherical particles, remember, spherical of any size, are going to be our small raindrops like drizzle or our perfectly spherical hailstones, and our ZDR is going to be 0. So if you're looking at radar and your ZDR is 0, you know that you're looking at spherical objects. Everything is the same shape and everything happens to be a sphere. Next, if we have small non-spherical particles, that would be like your raindrops, like this guy, or your snowflakes. Those are going to tell us that the ZDR is greater than 0. So your large ZDR values. That's because we have more of the horizontal plane being intersected than the vertical plane. So that increases our ZDR. Contrarily, if we have more particles aligned in the vertical axis, like conical graupel, this is actually quite common to see here in Pennsylvania in the winter months, your ZDR is going to be negative or less than 0. It's pretty rare to see ZDR that's negative. So if you do see that, you're lucky because it's not that common to see ZDR that's less than 0. That usually happens when particles are oriented vertical, and that doesn't happen a lot. That happens, of course, when we have conical graupel like this image on the right, or if we have debris that's somehow oriented in the vertical, or other things in the atmosphere, but it's not that common, right? Because usually we just have rain that's fat and flattens out, or we have spherical drops or spherical hailstones. So usually you're going to see ZDR close to 0 or ZDR greater than 0. But if you see ZDR less than 0, things are oriented up and down, which is kind of odd. Next, let's look at some correlation coefficient applications. So CC is usually the abbreviation for correlation coefficient. And usually we can see the melting layer, which we call the bright band. So our radar is at the center of this image here. And remember, close to the radar, we're close to the surface. As we get further out, we go higher in the atmosphere. So sometimes you'll see this ring as we enter the winter months. And this is actually telling us, remember that CC tells us diversity of shapes, diversity of composition, diversity of particles in the scattering volume. So when we see this brightness in the CC, we're actually getting lowerings in correlation coefficient, which means we have more diversity. So correlation coefficient goes on a scale from 0 to 1. If it's 1, everything is the same. If it goes below 1, that means we have diversity. So looking at yellows, we have less than 1 values. So we have lower values, which means we have some diversity. So what's happening here is we above this ring here, remember above is further away from the radar because the radar beam goes up in the atmosphere. We have snow. Everything is snow. Everything is the same. So because everything is the same and everything is snow, it's all the same color, all the same correlation coefficient. As we go down in the atmosphere, we get closer to this radar, we get to this point where something weird is happening. And this is actually where we have melting of that snow. So we're getting warmer, snow starts to melt. So in this ring, we have a combination of melting snowflakes, we have a combination of rain, we have a combination of snow that hasn't melted yet. And we have, since we have rain, liquid water, and snow, which is ice, all together in the same elevation, that is increasing our diversity of shapes, diversity of composition, diversity of particles. So our correlation coefficient is lowered. And then as we get even lower, now everything has turned to rain because it's all melted. So now everything has turned to rain, it's all the same, and then our correlation coefficient goes back up to 1. So it's a little bit complicated again because you have to think in that 3D space, but it looks like a ring because of the radar going up in atmosphere, but realistically there's a solid horizontal layer in the atmosphere where we have the melting. It's not a ring in real life. The ring is just because of the way the radar is set up and how it intersects the atmosphere. So we can see these phase transitions on radar. And again, we lower our CC due to diversity of shapes and composition. So I encourage you to look at the wintertime when we have some snow or rain moving through and see if you can find this melting layer or bright band. It won't always look like a perfect circle. Sometimes it'll get kind of funky, funky shapes, or maybe it'll only be on one side. So that's going to tell you what the heck is happening in the atmosphere. You know, maybe we have some front coming through, or maybe on the westerly side is different from the easterly side with the way that the atmosphere is set up for that day. So I encourage you to take a look at it and see if you can diagnose what's happening in the atmosphere, because it is really interesting to see these kind of transitions and phase transitions happening. So next, we're going to talk about KDP, or our specific differential phase application, and this is for heavy rain and wet hail detection in this specific example. Remember, our KDP looks at the non-spherical stuff, so anything non-spherical. And in this example, co-located with our high reflectivity, we also have really, really high values of KDP. So we're looking at non-spherical stuff. So either this is telling me we have a ton of really heavy, fat raindrops that are huge and have that flat bottom, and that's our non-spherical, or we've got a lot of small melting hail. So when hail starts to melt, it actually gets this hula hoop of water around the center of the stone. So if I have my hailstone, a hula hoop of water starts to form around the center of the stone because of the centrifugal forces and the way it's falling, all that physics. And we get this loop of water around the stone, so it actually makes the stone have more orientation in the horizontal or X direction than in the vertical. So it makes our stone more non-spherical as it's melting. So with that, we get not only an enhancement in reflectivity, but we also get the enhancement in KDP. So very heavy rain or small melting hail. So that's what I diagnosed from this image. Turns out on this day, we actually had lots of small melting hail. This looks like snow, but it's not. It's actually hail. Oops, let's go back here. So if you're ever looking at radar, you see really, really enhanced reflectivity with KDP, be on the lookout for large, heavy raindrops or large amounts of small melting hail. Usually KDP values this high are kind of telling us that we have maybe something else going on in the atmosphere. So large amounts of small melting hail is pretty common to find with these very large enhancements of KDP. All right, so getting on to our last topic here, tornadic debris signatures. First, we need to, in order to identify the tornadic debris signature on radar, we need to identify that velocity circulation. So remember your training on identifying where it's rotation versus not rotation. Know where your radar is. You have to find where the radar is and then diagnose the red touching the green. Is it rotation? Is it convergence? Is it divergence? And then you can go from there. If you've identified that it's velocity, go to step 2. You're going to pull up your correlation coefficient, your CC, and it has to be co-located with the circulation. So remember, we lower correlation coefficient with diversity of shapes, diversity of particles. So tornadic debris obviously is going to be lots of diverse things. Could be trees, could be trees with damage from infrastructure. It's going to be a lot of different things. So we want to have our low CC co-located with the velocity. We also want to make sure that we have sufficient reflectivity. So make sure that there's at least decent reflectivity, greater than 35 dBz, co-located with 1 and 2, because you want to make sure that you're not looking at ground clutter or buildings or anything else happening. You want to make sure you're looking at something meteorological, which will tend to have higher dBz values. And then also look for that lowering in differential reflectivity. Remember that when we talked about ZDR near 0, we said that that was for stuff that's spherical, but it doesn't have to, everything doesn't have to be spherical for us to get a ZDR near 0. So for example, if we had a bunch of different particles and all of the orientations were all sorts of different directions, we had some vertical, we had some horizontal, we had some crisscross things, on average, the orientation of those shapes is going to be 0 because they're not all facing the same way. They're not all facing the same way. They're all kind of scattered about. So averaging them all out, we're going to have ZDR near zero. So that's why when you're looking at tornadic debris, you're going to have that ZDR near zero, even though we're not really looking at spherical stuff. So for example, we can see really, really strong rotation here, red touching green. We've already diagnosed the radar location to be down towards the right. So we can see rotation here going out and then coming back in, have that strong rotation at the center. We also see co-located with that very low correlation, which means we have a lot of diversity of shapes, different particles going on right there at the center of the velocity. Okay, let's see if it co-locates with our reflectivity. Yep, in fact, this looks like a hook. You know, we've diagnosed that hook echoes are common with supercells, and this hook shape tells me that there is rotation happening. And also, since we see all the CC and velocity, that this is where the tornado is. And then just verifying with ZDR that we have our lowering in ZDR near zero also co-located. So this is a classic tornadic debris signature. If you happen to be looking at all of these different things at the same time, either on your cell phone or on the computer, this is what you'd see if there were a tornado occurring and if it's producing damage. First, you know, look at your velocity. Is there rotation? And then we have our lowering in CC, our reflectivity hook, and then our near zero ZDR. So this is classic tornadic debris signature. This is the easy example of trying to find a TDS. This is from the El Reno tornado in Oklahoma. So very easy to diagnose tornadic debris signatures out in the plains. A little bit more complicated in Pennsylvania. So this also happened to be a photo taken at the time. It's really kind of hard to see with the resolution here, but when we are looking at our velocity, we can actually see what's happening too on the ground, which is our rotation tornado signature. So we can actually see TDSs here in Pennsylvania as well, even though they're a little bit more difficult to pick out with all the mountains and beam blockage that we have. So first, let's find our rotation, since that's the easiest thing to do. Our radar location is towards this corner, so towards the bottom left corner. So if we look at that and we intersect our rotation here, we can see that red is going away, green is going towards. We have this rotation, red touching green. Okay, good. We found rotation. Now let's see what else is happening. So at that same location, we can see it's a little bit harder to pick out and maybe clearly see the lowering correlation, but this is indeed a lowering correlation. We have more diversity, so our CC is being lowered. We also have it co-located with some higher reflectivities, and then harder to see, but we have some close to zero ZDRs happening in this area as well. So they're a little bit harder to pick out with Pennsylvania, given all of our different terrain elements, and sometimes these more severe rotating storms happen further away from the radar. So as you get further away from the radar, it's harder to see what's going on, of course, as Jonathan alluded to. But we can see these TDS signatures, just like this one, which is the idealized case in Pennsylvania. So keep your eye out if you're watching radar and you can spot rotation. See if you can find your tornadic debris signature, which does mean that there is a tornado and there is damage occurring with it. So with that, we're all done with radar stuff. We're just going to do a quick promo for becoming a Weather Ready Nation ambassador. Since you're all interested in this radar basics course, you probably are interested in weather safety and keeping your community safe. So if you are, Weather Ready Nation is basically an organization by the National Weather Service that's promoting safety messages and themes to stakeholders. So that could be stakeholders for your business, stakeholders in your community, the list goes on and on. You will engage with us, NOAA personnel, and have potential collaboration opportunities. You're going to serve as an example by educating your employees on workplace preparedness. And becoming an ambassador, you just visit this weather.gov/weatherreadynation or WRN/AMB-TOU. And if you become an ambassador, the expectations are that you yourself are going to set an example for being weather ready. yourself. So making sure you have your safety plan in place, making sure your employees have their safety plan in place, and setting that as a priority because safety always comes first. You're going to promote Weather Ready Nation key messages and outreach activities and provide these incentives to become weather ready to your stakeholders, and then share your success stories with NOAA. So if this is interesting to you and you want to promote weather safety messages to your community, to your stakeholders, please, please, please consider becoming a Weather Ready Nation ambassador. And you can email me with questions if you aren't sure about this or want to know more information. And with that, we will just wrap up here. Remember how to find us online. We're on social media, weather.gov/CTP. We can take any questions you have, so I'll invite Jonathan to come back up. And if you are passionate about radar, this didn't satisfy that itch that you have, we are actually in the works of creating an advanced Weather Ready Nation radar talk. So we will have another talk coming up here that's more advanced applications, getting even deeper into the advanced applications that we briefly talked about today. And then we also have our advanced Skywarn talks coming up here in the fall. So we had our basic talks in the spring. If you're interested in becoming a Skywarn spotter and want to know, take more of a deep dive into the atmospheric physics, we will be having our advanced talks coming up here shortly. We're also working on a winter talk, so advanced topics for the winter months, and that'll be coming here shortly. So keep an eye out for that if you're interested in learning more. And with that, we can take questions. So if you want to verbally talk to us, you can raise your hand and we can unmute you. Or if you'd rather just type in the questions box, feel free to do that. So someone asked, how do we find more about the advanced classes? If you go to weather.gov/CTP and go to the tabs at the top, there's a tab called local programs, and underneath there's a link to the Skywarn page, and from there you can find the advanced class info. We actually have our recordings from our advanced classes from previous years, so if you don't want to wait, you can watch those on YouTube, or you can wait until we start posting information about that. So I would just go to that page every so often and check for updates. We'll also post about it on social media probably about a week before the classes actually occur. So keep an eye out for that. It'll definitely be happening in the next couple months here.